Hi, my name is Taran Agnihotri, and today I'll be presenting Lab 4 oscillations. The problem we have is to predict the motion of a mass attached to an oscillating spring. Theoretically, if we know the force at play, we should be able to predict the motion of an object. This is made possible through the energy principle, which states if no work is done by an external force, the total energy in a system will remain the same, and Newton's second law of motion, in which we calculate acceleration by dividing the net force by the mass. Some formulas we will use in this lab include the formula for kinetic energy, the force of a spring, the potential energy of a spring, the force of gravity, the potential energy of gravity, the period of oscillation, and the formula for total energy. The experimental setup is a mass attached to a spring, which is released after some initial force. A camera is mounted facing the mass attached to the spring. Tracker is used to analyze motion, GlowScript is used to model and predict motion, and Microsoft Excel was used to generate the CSV file. Some assumptions that we make in this experiment are that the only two forces acting on the mass are the spring force and gravity. We also assume that no work is done by external force on the system containing the spring, the mass, and the earth. Air resistance is negligible, and the camera lens is not distorted. In the tracker model, we start at frame 5 and end at frame 103 for a total of 99 frames analyzed. With the frame rate being 10.53 frames per second, the frame dt was 0.095 seconds, giving us a total time analyzed of 9.405 seconds. It was calibrated with a length from the fixed attachment point to the center of the mass of 0.70 meters. And the axis was centered at the fixed attachment point with a negative direction of the y-axis pointing downwards. Here's a recording of the tracker. To find k-spring, we start with the formula for the period of oscillation. We can rearrange this to say t squared equals 4 pi squared times mass divided by k. This further rearranges to k equals 4 pi squared times mass over t squared. As we calculate the period from tracker to be 1.524 seconds and the mass given as 0.402 kilograms, we can use this formula to find k being 6.83 newtons per meter. For L0, we first start with F gravity equals F spring, meaning mg equals k L minus L0. Rearranging this, we get mg over k equals L minus L0. Further rearranging this, we get L0 equals L minus mg over k. Plugging the numbers for mg and k, we get that L0 equals 0.1226 meters. For the GlowScript code, I started by adding the system mass for the ball of the mass given, adding the ball's position vector to be the vector found through the tracker, the ball's velocity to be 0, g to be 9.8, the spring constant to be the constant we calculated, L0 to be L0 we calculated, L to be the ball's position minus the spring's position, L hat being L over the magnitude of L, and S being the magnitude of L minus L0. For K, potential energy of gravity, potential energy of the spring, and total energy, I used the aforementioned formulas of 1/2 mv squared, mgh, and 1/2 ks squared, as we discussed earlier. The total energy was just the sum of all the three of these energies. Continuing with the GlowScript code, the force of gravity was the vector with the ball's mass multiplied by the gravity. The force of spring is negative ks times L hat. F net is the force of gravity plus the force of spring, which we discussed were the only two forces. We use the velocity update formula for ball dot velocity and the position update formula for ball dot position. L was ball dot position minus spring position. L hat was L over magnitude of L, as we discussed earlier. And all the formulas for K, potential energy of gravity, potential energy of spring, and energy remain the same. Here's a recording of the GlowScript. Here you can see the change in energy versus time. As observed, delta E is 0. The x position in the model versus the experiment was very close. The same is true for the y position, which is just as close. What does it mean? For our system, the energy principle is justified. As shown, the change in energy remained at 0 for the duration of the experiment in the model. This shows that the energy was conserved and we're justified in using it. Using the x position, the period of oscillation is 1.646 seconds. Using the y position, the period of oscillation is 1.519 seconds. As a result of the initial force applied, the object's period of oscillation is longer in the x direction than the y direction, which gives it this variation. Some error sources and how we can improve. There is slight camera distortion, which we can improve, but we can be aware of. The tracker points were picked by hand, which could be slightly inaccurate, and the video quality was low, and this low frame rate might have led to inaccurate and less data points. Conclusion. If we know the net force or lack of forces acting on an object, we can predict its motion. Using the energy principle in conjunction with Newton's second law of motion allows us to calculate the total energy and force on an object. The total energy is the kinetic energy plus the gravitational potential energy plus the spring potential energy. In a closed system, delta E equals 0, and F net equals mass times acceleration. Using these, we can form accurate models to predict motion. Thank you.